So let's imagine that I'm here. This is me at the age, actually I'll do this right now. So let's say at the age of 31. And then I go into the future. So this is a line for the present. And then I go into the future. And this is me again. And this is now at the age of 71. So I've got 40 extra years. I even picked up a cane to help me walk around. And finally, I go even further in the future, and I'm being very optimistic. I'm going to go ahead and say this is at the age of 101. I live to be a centennial, and I'm sitting in a wheelchair, and I'm going to wave out at you. So that's me in a wheelchair at the age of 101. And we're going to apply that formula we've been talking about so much. Delta P equals Q times R. So I said Q is cardiac output, and we've got R is resistance. So we've got this formula, and let's say I go to the doctor's office, and I go today, and I go in 40 years, and I go again when I'm 101. And today they tell me my blood pressure is 120 over 80. And actually, I went not too long ago, and that's pretty much what they told me it was. And I go in the future, and in 40 years, they tell me it's actually gone up. My blood pressure is now 150 over 90. And in fact, I go again when I'm 101, and they say it's 180 over, let's say, 105. So the blood pressure is rising, and that's basically what I'm told. And they say, well, you got to make sure you eat well and exercise, and that should help your blood pressure. And I'm left wondering what the connection is between the two. So let's figure out what that connection is exactly. So my blood pressure, I just said, is 120 over 80. And if I want to figure out my mean arterial pressure, so my mean arterial pressure, meaning the average pressure in my arteries, I can actually use my blood pressure to give me a good guess as to what it's going to be. So I know that I spend about a third, my mean arterial pressure is going to equal a third times my systolic, because I know I spend about a third of the time, my heart does anyway, spends a third of its time beating, and it spends 2/3 of its time relaxing, and the relaxing pressure is the diastolic pressure, that's 80, and so that works out to about 95. And so that's how I came up with that 95 number, and that's also why it's not exactly 100, which is what you'd think an average would be between two numbers, but it's because we don't spend the exact same amount of time in systole as diastole. So then if I wanted to figure out here, it would be 1/3 times 150 plus 2/3 times 90, and that works out to 110. And if I wanted to do it at the age of 101, my mean arterial pressure would be 1/3 times 180 plus 2/3 times 105, and that works out to 100 and, let's see, 60 and 70, 30, 130. So I figured out my mean arterial pressure, and then I also, let me write that with a line, I also need my mean venous pressure, because we know we're going to have to subtract the two from one another to get the delta P, delta meaning the difference. So mean venous pressure right now is about 5. And let's assume, this is one of a few assumptions we're going to make, let's assume that it doesn't change, that over a few years it really stays around the same, it's about 5. Well then if I know that, my delta P is easy to figure out, right? I can just take 95 minus 5, and that'll get me 90. And I can take 110 minus 5, and that's 105. And I can take 130 minus 5, and that's 125. So I figured out my delta P, which is basically my mean arterial pressure minus my mean venous pressure, and that equals my delta P. Okay, so far so good. Now let me change colors to figure out my Q, my flow. And right now I have, let's say, a stroke volume. I'll write it up here. Stroke volume, meaning each time my heart beats, about 70 milliliters of blood go out. So each time my heart beats, it sends out to the rest of the body 70 mLs of blood. And that's based on the fact that I'm about 70 kilos. And my heart rate is about 70, very relaxed heart rate. And let's assume, just as we did with the mean venous pressure, that that doesn't change. So this is not going to change over time. So this works out to about 5 liters a minute, because Q is simply, let me write that here, Q is simply SV times HR. And so I'm just multiplying those two numbers together, and I get about 5 liters a minute, and it doesn't change over time. So 5 liters a minute here, 5 liters a minute here. And I should probably mention all of my pressure units should be millimeters of mercury. I didn't write that just to not clutter up the board, but let's just assume that, well, it's not assuming, it is millimeters of mercury. So now, using my equation, I can now say, well, delta P, and actually maybe up here I should even change this to be blue so that I'm consistent. So delta P equals Q times R. So if delta P is 90 and Q is 5, my resistance equals 18, right? I mean, it's just a bit of math that I did very quickly, but 18 times 5 is 90. And here I could figure it out. 105 divided by 5 would give me a resistance of 21. And here I would figure out that it's going to be 25. So one thing that I've been told by my doctor is that my blood pressure is rising. And two things that I've assumed are that my mean venous pressure are the same and that my cardiac output is the same. And if I assume that, and that's definitely not true for everybody, but if I assume that for me, then that means that my resistance has gone up. Over time, my resistance has gone up. And let's now change screens and figure out how that could possibly happen. So let me draw myself out again. So I've got 3 versions of me. I've got the present me at the age of 31. I've got the future me with a cane at the age of 71. And I've got the really old version of myself living at a ripe old age of 101. Waving, in fact. So 3 versions of myself. And if I was to draw out my arterial tree, let's say a simplified version of my arterial tree, let's say here's a vessel coming through and I've got, let's say, another vessel and this branch is here and I've got a third vessel and this branch is here. Right now my arterial tree looks pretty good, pretty clean, and that's why my resistance was 18. You know, blood is flowing through very smoothly. It's going out this way to feed the kidney and maybe my ears and my eyes and my foot. And it's basically making its way through no trouble. Now at the age of 71, something happens. Actually, let me just draw a little divider line. At the age of 71, something happens. I have, let's say, the same arterial tree. I'll try to draw it the same way. Except now I've been eating for 40 years, you know, foods that are not the best, and I certainly haven't exercised a whole heck of a lot. I haven't gone to the gym very often, and now I've got buildup of plaque. So let's say I've got a plaque right there, and I've got a plaque, let's say another one right there, and let's say I have a plaque right there. So I've got 3 little plaques, and we'll get into plaque and what it's made of exactly in a future video, but for the moment, just think of it as something that's blocking up that vessel. And it's usually made of fatty substances and macrophages and cells that have died and all sorts of kind of basically crud that fills up the vessels. And so because it's filled up the vessels, now here my radius got smaller. My vessel radius, and here it got smaller. And over here it got smaller. So blood, as it's flowing through, is having a tougher time getting through because the radius is smaller in these spots. And as you know, if you calculate total resistance, and that's what actually this is, total resistance, the total resistance will start to slowly climb up. And in this case, maybe it climbs up to 21. And now years go by, let's say 30 more years go by, I'm now in a wheelchair, and I continue to not eat so well. I eat, you know, the same sort of fast food that isn't healthy for me, but I can't possibly stop because I find it tasty. And at the end of the day, my vessels look like this. I have that same one as before, let's say, and let's say this one actually grew longer. So instead of just being part of the vessel, let's say it's huge now. This one got very big. And let's say this one up here actually continued and grew a little bit as well. But I also picked up another one right here, let's say, and I also got one right here. So I have a few more blocks in the road. And so now my blood is having a real hard time getting through because it's got more obstruction to flow. All my paths have a smaller radius. And we know, and I've mentioned a number of times now, about the relationship between a radius and resistance, and that as the radius everywhere gets smaller, the resistance is going to get bigger. And so my total resistance here, let's say, is about 25. So now you can see how eating a certain way and not exercising is going to lead to potentially developing these plaques that act as roadblocks and get in the way of blood flow. And the reason that that's a problem is that as we see now, the radius gets smaller, the resistance goes up. And in the previous slide here, we actually can see now that as the resistance goes up, assuming that the other things kind of stay the same, your blood pressure can go up. And so when you hear in the doctor's office that you have a blood pressure of a certain number over a certain number, that's one thing that we can measure. And what it tells you is a little bit of information about some of the things that we can't easily measure, such as resistance. So let's stop there and we'll pick up.